Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. In this video, my topic of discussion is ferroelectricity. So today we are going to discuss about one functional material. Actually, we can call this ferroelectric material as functional materials. Why we call them as functional materials? Because these ferroelectric materials, they have got many applications. They are used as sensors, they are used as actuators. Okay, so like this, they have many day-to-day applications, and these are, of course, application-oriented materials. These are special type of materials which has some unique characteristics. So that's why we can also say that call them as functional materials. Also, we can call them as engineered electric materials. So this ferroelectric materials, they'll come under engineered electric materials. And here, when we try to discuss what exactly are these materials, so what are the special features or properties associated with ferroelectric materials, and what are the different applications of this material, so it will all come under this ferroelectricity. So in order to study different characteristics of these ferroelectric material, it will be taken as ferroelectricity. So before going into detail about that ferroelectricity or properties associated with ferroelectric materials, or how special these ferroelectric materials, first we should know what exactly are ferroelectric materials. So, in my previous video, I have discussed a lot about dielectric materials. So, what we have discussed about dielectric materials, when we are talking about dielectric materials, we said that these materials generally they are insulators. They don't have any free electrons. Here, electrons are very tightly bound to their nucleus. But what we are going to observe here is these, when we place these dielectric materials in external electric field. So when we consider our dielectric materials, how we'll apply electric field to this dielectric material? Generally, we'll place them in between the capacitor plates. So dielectric materials, they are placed in between the capacitor plates, and then we are going to apply electric field. So these are positive charges, these are negative charges. And here these dielectric materials will have development of polarized charges or induced charges on the plane surfaces of dielectric. So these materials, they have this property of getting polarized once we apply external electric field. So these are about our dielectric materials. Then in what way are these ferroelectric materials different from dielectric materials? So generally we can say that these ferroelectric materials are nothing but dielectric materials. And what we are going to say here is these materials, they possess spontaneous polarization. So this is very important term related to ferroelectric materials. Here we are saying that these dielectric materials, they possess spontaneous polarization. What do you mean by spontaneous polarization? Polarization which is spontaneously developed within the material, even when we take out our electric field. So we know that in dielectric materials, as long as we apply electric field, we have polarization. But what we are going to observe here is, suppose if I replace this normal dielectric material with ferroelectric material, of course when I apply electric field, it has got a polarization. But once I remove electric field, then we'll observe that its polarization will not drop to zero. So even when external electric field is brought to zero, then polarization which is developed in this material, it will not come to zero. So it means that it is retaining polarization. So that polarization, it is called as spontaneous polarization. So these materials are special, as I said. In what way they are special, or in what way they are different from normal dielectric materials? They possess spontaneous polarization even in the absence of electric field. Even if we take out our electric field, if we bring our electric field back to zero, they possess some polarization. And such materials, they are called as ferroelectric materials. As I am telling you, these are functional materials which have got many applications. And then now let us see, we have discussed about dielectric materials in a previous video, and we have seen that dielectric material examples, we can have polar as well as non-polar dielectrics. So when we talk about polar dielectrics, we have water, hydrogen chloride, ammonia, and of course methyl chloride. So like this, we have many examples for polar dielectrics. Then coming to non-polar dielectrics, which consists of monoatom atoms. Okay, their molecules, they consist of mono atoms. So if we consider, we have hydrogen molecule and then nitrogen molecule, then we have carbon dioxide, so they will come under non-polar directories. But if we try to take examples of these ferroelectric materials, as we said, they are special type of materials. Now coming to first example is Rochelle salt, and it's the first ferroelectric material discovered. So this Rochelle salt we can take in as first material which has been discovered. And what is the composition of this Rochelle salt? As you can see from its composition, which is given in this PPT, so it consists of sodium, potassium, carbon, hydrogen atoms. Okay, so it's a salt which consists of sodium, potassium and carbon. Okay, so as I said, this is the first material in which ferroelectric behavior has been observed. Then coming to next example is potassium dihydrogen phosphate. So potassium dihydrogen phosphate, and what is the formula? KH2PO4, or simply it is called as KDP. K stands for potassium, H2 stands for dihydrogen, and phosphate is PO4. And coming to third example, very popular example for ferroelectric material, barium titanate. And what is the formula for barium titanate? It is taken as BaTiO3. And the next is just similar to barium titanate. We have one more example, which is lithium niobate, which is LiNbO3. And then of course potassium niobate. So there are some more examples of ferroelectric materials, but we have taken very few of them. And here what we are going to observe here is, as you can see in the end, we'll try to observe this phenomenon of ferroelectricity in barium ion. By taking structure of barium titanate, we are going to observe what are the properties exhibited by a ferroelectric material. Now we'll come into ferroelectricity. What is ferroelectricity? Ferroelectricity is nothing but discussing about different unique properties exhibited by ferroelectric materials. Now coming to first property. So if I take this first property of ferroelectric materials, so here, as we already told that what exactly are ferroelectric materials, we define them as dielectric materials which possess spontaneous polarization even in the absence of electric field. Now what you're going to observe here is this spontaneous polarization existing within ferroelectric material, it is a function of temperature. So spontaneous polarization associated with a ferroelectric material, even when electric field is brought to zero, it is a function of temperature. When we start applying the temperature to ferroelectric material, when we start heating ferroelectric material, then spontaneous polarization associated with ferroelectric material, it is going to change. And how it is going to change, that we can understand in this first figure. So if you look at this first figure, so what we have taken on x-axis, I have taken temperature T. Okay, with respect to this temperature T, we are taking polarization associated with ferroelectric material. And what we are going to observe here is, first, what is PS? PS is, of course, at normal temperature, when we go for normal room temperature, when electric field is reduced to zero, then there is some spontaneous polarization associated with ferroelectric material, and it is denoted by PS. So what is our PS at room temperature? If you take temperature at which ferroelectricity exists, so at that ferroelectric temperature, here polarization associated, spontaneous polarization associated with ferroelectric material, it is PS. Now after that, what I have done, I started increasing temperature. So when you start heating ferroelectric material, then what we are going to observe here is, this is the shape of the curve followed with respect to temperature. So slowly this spontaneous polarization value, it keeps on decreasing. So decreases, and then what you are going to observe here is, there is actually this temperature, this is equal, T is equal to Tc. So there exists one temperature called as Tc. So it is represented by Tc. What happened to spontaneous polarization? Spontaneous polarization has become zero. So for temperatures below Tc, there is spontaneous polarization associated with ferroelectric material. But once we come to this temperature, which is Tc, and value of Tc, temperature at which spontaneous polarization is becoming 0, it will be different for different ferroelectric materials. Suppose if I take a barium titanate, then its Tc value will be of 1 value, and then for other materials they'll have other Tc values. So depending upon what type of ferroelectric materials we are taking, the Tc value is going to change. So what we are saying here is, as we increase temperature, spontaneous polarization keeps on decreasing with temperature, and there exists one certain temperature Tc. What happens to spontaneous polarization? Spontaneous polarization is becoming 0. And what exactly is Tc? So this temperature Tc, it is called as Curie temperature, after the name of scientist Curie, who has observed this phenomena. So this Tc, it is called as Curie temperature. And what exactly is happening at this Curie temperature? Spontaneous polarization associated with ferroelectric material is going to 0. It means that ferroelectricity, it exists only below Tc. Above Tc, ferroelectricity is not there. So your material, it is not ferroelectric. Then what exactly is happening above Tc? Above Tc, what we are going to observe here is, there is transition of material from ferroelectric to paraelectric. So how we are going to define this Curie temperature Tc? Tc, it is defined as temperature at which ferroelectric material gets converted to paraelectric material. What exactly is paraelectric material? In paraelectric material, of course, when we apply external electric field, it will undergo polarization, but it does not possess any spontaneous polarization. So there won't be any spontaneous polarization associated with paraelectric material. So that's why at T is equal to Tc, called as Curie temperature, that there is transition of material from ferroelectric to paraelectric. So this is the first feature exhibited by ferroelectric material when we are talking in terms of spontaneous polarization associated with ferroelectric material. Now coming to this second figure given here. So for this we have to take our second property. So this is our second property. Now as we have seen that below Curie temperature, your material, it is in ferroelectric state. And below Curie temperature, what we are going to observe here is dielectric constant associated with ferroelectric material. It shows variation with electric field. So what we are saying here is, below Tc, below Curie temperature, so dielectric constant of ferroelectric material, it is going to change, or it is function of electric field. Whereas at temperatures greater than Curie temperature, of course, dielectric constant is function of temperature. Now, to understand this, I'll go back to our this slide. So, if you look at this temperature, of course, here on y-axis, I have taken susceptibility. But in place of susceptibility, I can also take dielectric constant epsilon r. So, we can take epsilon r. Also, we can take electric susceptibility. And on x-axis, we are taking temperature. And what we have done, we have shown variation of dielectric constant or susceptibility with the temperature. Suppose I have taken dielectric constant, then what you are going to observe here is, as temperature is increased, what is happening to dielectric constant value? First, it is increasing, and then once I reach to temperature which is equal to Curie temperature Tc, what is happening to dielectric constant? Dielectric constant, it has gone to its maximum value. Okay. So dielectric constant associated with ferroelectric material, it will have its maximum value at temperature Tc. What is Tc? Curie temperature, where there is transition of material from ferroelectric to paraelectric state. And as long as your material is in ferroelectric state, with increase of temperature, you will find that its dielectric constant is increasing. This is the property, or in order to make out difference between ferroelectric and paraelectric material, we can say that below Tc, as long as your material is in ferroelectric state, its dielectric constant, it is going to increase with temperature. But once we reach Tc, dielectric constant, it has gone to maximum value. And we know that at Tc, there is conversion from ferro to para. So here it is in ferro state and it is in para state. Once your material has converted to para state, with increase of temperature, what is happening to dielectric constant? Dielectric constant, it is reducing and reducing. decreasing. So now if we want to differentiate between ferroelectric and paraelectric, we can say that in ferroelectric, with increase of temperature, dielectric constant is increasing, whereas in paraelectric state, with increase of temperature, dielectric constant is decreasing. So, and of course at Tc, there is transition from ferro to para, and at this particular temperature Tc, we have maximum dielectric constant. And then coming to third important feature of ferroelectric material. Suppose if I have gone at temperatures greater than Tc, then this ferroelectric materials, the dependence of ferroelectric materials on temperature, it is not simple, but it is complicated, and it is given by one particular law called as Curie-Weiss law. So after the name of two scientists, Curie and Weiss, okay, which have taken this concept of ferroelectric material and its dielectric constant with temperature. So what you are going to observe here is, once if I take a ferroelectric material and if I heat it at temperatures greater than Tc, then dependence of dielectric constant of that ferroelectric material on temperature, it is given by Curie-Weiss law. And according to Curie-Weiss law, how this dielectric constant is dependent on temperature, it is given as epsilon r is equal to C by T minus Tc. So here, dielectric constant of ferroelectric material, it behaves in a complicated manner once we go to temperatures greater than Tc. And what is C? C, it is called as Curie's constant. And this particular variation of dielectric constant with temperature above Tc, let me tell you one thing, important thing. This particular equation, it holds good for ferroelectric materials only at temperatures greater than Curie temperature. And of course, this variation with temperature, it is taken as Curie-Weiss law. So not just linearly proportional or exponentially proportional, but here variation of dielectric constant with temperature, it is given like it obeys complicated law, and that law, it is nothing but Curie-Weiss law. And of course, as I told, this is a temperature, it holds good only at temperature T greater than Tc, where Tc is Curie temperature. What is Curie temperature? Temperature at which ferro gets converted to paraelectric. Now coming to fourth very important property of ferroelectric material. This is very important property, and it also tells us what do you mean by having spontaneous polarization even in the absence of electric field. And they will make us better understand difference between dielectric material and ferroelectric material. Now what you're going to observe here is, we are saying that this foremost like very important feature or very unique feature that can be shown by ferroelectric material is, it exhibits hysteresis curve. So now, what exactly is this hysteresis curve? Very important feature and application of ferroelectric material is because of its exhibiting hysteresis curve. So first we'll try to see what exactly is hysteresis curve. So as you can make out that this hysteresis curve, of course it is a curve, okay, and how we are going to get this curve? In order to get this curve, I have taken electric field on x-axis, and then we are taking polarization on y-axis. So what we are doing, we are taking electric field on x-axis and polarization on y-axis. So here hysteresis curve is nothing but PE curve, and there is another name for this hysteresis curve. This hysteresis curve, it is also called as hysteresis loop. So it is also called as hysteresis loop. And what exactly is this curve? It's the curve taken between electric field and polarization. So we are applying electric field to ferroelectric material, and with respect to this applied electric field, how polarization associated with ferroelectric material is going to change. That particular curve, it is called as hysteresis curve. And of course, here there is one point. Here we are talking about hysteresis curve being property of lacking of polarization behind the applied electric field. That we'll come to know once I discuss about this hysteresis curve. So I'll come back to this point first when we discuss about this curve. Now, in order to understand this curve, so slowly again one by one, I'm going to draw this curve here. So here, if I try to draw this curve again, so this is our x-axis and this is our y-axis, and of course this is negative axis, both are negative axis. So what we are doing on x-axis? On x-axis we are taking electric field E. So on x-axis we are taking electric field E. on y-axis we are taking polarization. Okay, so we are taking polarization. Now first I have taken a ferroelectric material and I'm starting from this point, and as you can make out that at this point, we can also say that this is 0 point. What do you mean by 0 point? Electric field is 0, polarization is also 0. Okay, so here there are no dipoles. So if there are no dipoles, then there is no dipole moment. So we are at this point where electric field is 0, polarization is also 0. Now after this, I started increasing strength of electric field. So when we started increasing strength of electric field, then what we are going to observe here is this curve, it is going to go in this path. Okay, so this is the path taken by polarization versus electric field curve. So first we started from origin where electric field is 0, polarization is also 0. And once we start increasing electric field, what happened to polarization? Polarization is increasing, slowly it is increasing. And then what you are going to observe here is, once it comes to one particular value, it comes to saturation. So what do you mean by coming to saturation? Coming to saturation means, even if I increase strength of electric field, so even if we increase strength of electric field, then there is no change in polarization value. And this polarization value, it is called as saturation polarization, or it is also called as spontaneous polarization. So what is PS here? So if you take this curve, now we have come to PS value. So this PS, it represents saturation polarization. Okay. So here what I have done, we have started applying electric field to a ferroelectric material. So when we start increasing this electric field, what happened to polarization? Polarization, it is increasing, and then it will go to one constant value. So what do you mean by coming to constant value? Even if we increase our electric field, then what happens to polarization? Polarization value, there won't be any change. It means that your material, it has got polarized to its maximum value. It has come to saturation. So this PS, it is called as saturation polarization. Now, after coming to this point of saturation, what I have done now? Now I am reducing my electric field back to 0. So what we are doing? We are reducing our electric field back to 0. Then obviously what this ferroelectric material should do? It should go along its initial path back. So it should follow this path, okay, and then your polarization, it should decrease. So what we are doing? We are reducing E to 0. So we are reducing E to 0. When we start reducing E to 0, actually your material, it should take its initial path, and with the decrease in electric field, polarization should also decrease, and again it should come back to its initial point. What is this initial point? When electric field is 0, polarization should be 0. But what you are going to observe here is, when we are reducing our electric field to 0, ferroelectric material, it won't follow this path, but it will create a new path and it will go like this. Okay, so what I have done? So here polarization, it has created new path. So now what is happening to polarization? If you see here, when I am reducing polarization to 0, then of course polarization is decreasing, but not along this initial path, but it started decreasing along this new path. And if you consider this point, at this point your electric field has become 0. So electric field, it has become 0, but is our polarization 0? Polarization is not 0. There is some polarization retained by ferroelectric material, and this polarization, it is called as a relative polarization, or simply it is called as a retentivity. Simply it is called as retentivity. So what is retentivity? Retentivity is polarization retained by ferroelectric materials even when electric field is reduced to 0. So here, when what we are saying here is, once we go to saturation polarization, if we bring our electric field back to zero, then at zero electric field, polarization is not zero. It is retaining some polarization. That polarization it is called as retentivity or remnant polarization. So this PR, it is called as retentivity, or it is also called as remnant polarization. And this is very important property of ferroelectric materials. Because of this property, they are used in memory devices. So in memory devices, because even if your power goes off, it is going to store data for some time. So for those memories, non-volatile memories, where there is no loss of data when power goes off, for that we make use of these materials. Okay, so here we are at this point where there is some polarization retained by ferroelectric material even when electric field is reduced to zero. That polarization is called as remnant polarization. Now when your electric field is zero, then what I have done at this point, I started applying electric field in negative direction or in opposite direction. So I started applying electric field in opposite direction. So here you are applying negative electric field. Then what happened to polarization? Now polarization still started decreasing. And then at one particular electric field, this electric field I am calling it as minus EC, because we are applying electric field in the opposite direction. So this is negative electric field. So there exists one negative electric field. At that negative electric field, what happened here? Your polarization has become zero. So polarization has become zero, but electric field is not zero. Okay, and this minus EC, it is called as negative coercive field. So it is called as negative coercive field. Okay, and what is negative coercive field? We can say that negative coercive field is the electric field required to bring positive remnant polarization to zero. So what exactly is happening at coercive field? This remnant polarization is becoming zero. So how we are going to define this EC? So what is our EC? Of course, if it is minus EC, it is called as negative coercive field, or simply it is called as coercivity. So it is called as coercivity. PR, it is called as retentivity. So what is coercivity? It is negative coercive field, which is the field required, negative field required in order to bring positive remnant polarization to zero. Now, after coming to this point, I didn't stop applying negative electric field. Still, I am continuing to apply negative electric field. Now, from zero state, your polarization, it will start increasing in negative direction. So, here, polarization is increasing, but it is increasing in negative direction, and then increasing. Polarization, again, it goes to saturation. So again, polarization, it goes to saturation. So here, it has gone to saturation. So here, what we are going to observe here is, so in this direction, we have negative polarization. So increases, and this polarization, it goes to saturation. Again, like even if I apply negative electric field, then there won't be any increase in polarization value. So it means that polarization, it has come to saturation, and this is called as minus PS. So negative saturation polarization. So no matter if I keep on increasing negative electric field, there won't be any change in PS value. Okay, now after coming to this point of negative saturation, again I start decreasing negative electric field to zero. So what I have done, I have started decreasing negative electric field to zero. Then what you will observe here is polarization, negative polarization, it starts decreasing, and then it follows this path. Okay, it follows this path when we are reducing our electric field to zero. And what we are going to observe here is, at this particular point, again we have come to this point of zero electric field, there is some polarization retained by ferroelectric material, and this polarization, it is given as minus PR. So what is PR again? PR is retentivity, or it is also called as remnant polarization, but this is negative remnant polarization. Okay, and what is negative remnant polarization? So it's the polarization retained by ferroelectric material even when electric field is brought back to zero. So at this point again there is polarization when electric field is 0. At this point polarization is 0 but electric field is not 0. And if I start applying positive electric field after coming to the state of this negative remnant magnetization, then slowly polarization, it keeps on increasing in this direction. It increases and again it goes to positive saturation. So it is going to follow this path when we start increasing our electric field in positive direction. So again it goes to saturation, polarization. After again coming to this point, if I reduced my electric field back to 0, then it will take this path. Again, you will have positive remnant polarization at 0 electric field. If I apply negative electric field, then again it goes in this path, and then at one particular electric field, your positive remnant polarization will become 0. That particular electric field to bring polarization to 0, it is called as coercive field or coercivity. And if we still apply negative field, again it goes to negative saturation. And then after that, when we start reducing this negative field to 0, then at one particular, at a 0 electric field, there is some polarization retained by ferroelectric material, which is negative remnant polarization. And when we start applying positive field, again polarization increases and it goes back to its positive saturation. So this is our cyclic process. So here we'll say that hysteresis curve, it's a cyclic process. So first property here is it's a cyclic process because with respect to your increasing or decreasing of electric field, it is going to follow same path. And one more point what you're going to observe here is, second feature of this hysteresis curve is it represents irreversible property. So it represents irreversible property of ferroelectric material. So it is irreversible property of ferroelectric material. Now why it is called irreversible property of ferroelectric material? Because what is the starting point? Starting point is this, where electric field is 0, polarization is 0. But once we start applying electric field, once it has gone out of the state of 0 electric field and 0 polarization, we cannot come back to this original state. So if we reduce our E to 0, P is not 0. And if P becomes 0, then E is not 0. So we may not come back to the stage of polarization becoming 0 when electric field is 0. So that's why it is called as irreversible property of ferroelectric material. And one more thing what we have to understand here is simply polarization is following electric field. So that's why we'll say that there is lagging of polarization behind the applied electric field. And whatever curve or loop we are getting, area of that loop, it is called as loss, dielectric loss associated with ferroelectric materials. So this is about very important feature exhibited by ferroelectric material, which is nothing but hysteresis curve or hysteresis loop. Now what I have done, of course, now again we are talking in terms of temperature. We know that we have seen that when we keep on increasing temperature, then there exists one temperature. So here I have taken dielectric constant. So there exists one temperature Tc, and this temperature Tc, it is called as Curie temperature. And what is Curie temperature? Where ferroelectric material gets converted to paraelectric material. Then above Tc, when I keep on increasing the temperature, what you're going to observe here is shape and area of hysteresis loop, it is dependent on temperature. So whatever shape, we got the shape, right? So leaf shape. So shape and as well as area of this hysteresis loop, it is going to change with temperature. Now if I start applying temperature to ferroelectric material with respect to temperature, shape of the loop as well as area of the loop is going to change. And what do you mean by area of loop changing? So what you're going to observe here is height as well as width. So when you talk about x as well as y axis, so height we talk about polarization, width we talk about electric field. So height and width of this loop, it is going to decrease with increase of temperature. So height and width of the loop, it will decrease with increase of temperature. And once we go beyond temperature Tc or Curie temperature, where there is conversion of ferroelectric material to paraelectric material, what happens to loop? Loop, it merges into a straight line. So what is that hysteresis curve exhibited by paraelectric material? It's a straight line which is passing through origin. And this is for paraelectric material. So paraelectric material does not give us hysteresis loop, it will be a straight line. So what we have to understand here is the area of the loop, that is height and width of the loop, it is going to increase with increase of temperature, and once ferro gets converted to para at Curie temperature, that loop it merges into a straight line. And of course, the spontaneous polarization which is associated with ferroelectric material, it is dependent on certain factors. Of course, we can make out that we have seen spontaneous polarization. So it depends upon what is the shape of hysteresis loop. Some ferroelectric materials, they exhibit small hysteresis loop. Their area will be small, whereas some other ferroelectric materials, they'll exhibit large hysteresis loop area. So that's why depending upon shape of hysteresis loop, obviously spontaneous polarization value is going to change, and it is also going to change with temperature, which just we have discussed. Okay, and it also depends on dimension of the material, because suppose I have taken a material and if I am reducing its dimension, then obviously electric field parameter will be different. So when electric field parameter is different, then obviously polarization value will also change. And also it depends upon thermal and electrical properties of material. So even spontaneous polarization value, it is dependent on thermal and electric properties of material. So these are some of the properties of ferroelectric materials. Now we try to understand better about a ferroelectric material by taking one example. And what is that example? I have taken barium titanate. So we try to see how there is conversion of ferro state to para state at T is equal to Tc by taking structure of barium titanate. So now if you take this barium titanate, which is one good example of ferroelectric material, okay, if you take, and what is the formula for this barium titanate? BaTiO3. So if you take this barium titanate, it consists of three different types of ions. One is barium ion. So here we have barium ion, and then we have titanium ion, and of course we have oxygen ion. So there are three different types of ions. And what we are going to observe here is, this is the structure taken for barium titanate at T is equal to Tc. Okay, and what is the value of Tc for barium titanate? Curie temperature for barium titanate is 120 degrees Celsius. So Tc value is 120 degrees Celsius. It means that below this Tc, your barium titanate, it will behave as ferroelectric material. Above Tc, it will behave as paraelectric material. And what you're going to observe here is this particular structure, which I have shown in the figure. So this structure is cubic structure. So this represents cubic unit cell of barium titanate. Okay, and this structure is present only at temperature T is equal to Tc or T greater than Tc. And in this particular structure value, it is in which state? Paraelectric state. So your barium titanate, it is not in ferroelectric state, but it is in paraelectric state. Now we'll see what exactly is happening, why it is getting converted to paraelectric state. Once we go temperature beyond Tc, we are going to observe here. Now first we try to understand structure when it is in paraelectric state, or when we are applying temperature greater than Curie temperature. Then we'll try to correlate with its structure below Tc, where it is exhibiting ferroelectric behavior. Now as you can see, this is the cubic unit cell of barium titanate at temperatures greater than Tc, or when your barium titanate, it is in paraelectric state. Now if you consider distribution of ions, so in this cubic unit cell, where are the barium ions? Barium ions, they are present at the corners. So 8 corners of cubic unit cell, we have barium ions. And then what about this oxygen ion? So here we have 6 oxygen ions which are present at the 6 phase centers. So at the phase center, so at the center of each phase, we know that cube, it has got 6 faces. So these are faces of cubic unit cell, and this is the centers. These are called as phase centers. At the center of phase of each phase of this cubic structure, we have 1 oxygen ion. So like that, we have 6 oxygen ions. And then at the body center of cubic unit cell, there is 1 titanium ion. So if we take cubic unit cell of barium titanate, it consists of 8 corner barium ions, okay, which are positive ions, and then 6 oxygen ions. Where the 6 oxygen ions are present, they are present at 6 phase centers. And of course, there is one titanium ion at the center, and this titanium ion is positively charged. And of course, in this figure, we are showing as if this barium ions is well separated from this oxygen ion, or this titanium ion is well separated from oxygen ion. But actually, all these ions, they will be very much closer to each other. And what you are going to observe here is, if we consider their structure. So if I take this unit cell, right, here we have our barium ions. And when we consider this oxygen ion, then they will be attached to this barium ions. Okay, even this body center titanium ion will also get attached to this negative oxygen ion. Okay, so here when it is in cubic state, then this barium ion, it is touching this particular oxygen ion. Even titanium ion is also touching this oxygen ion. So here, positive ions and negative ions are not separated from each other. Because they are not separated from each other, they have one symmetrical structure. That symmetrical structure is cubic in itself. Because positive ions and negative ions are not separated, it means that there is no dipole. So when there is no dipole moment. So no dipole moment means your material, it is in paraelectric state. Whereas if I am at temperature below 120 degrees Celsius, then your material, this particular barium titanate, it has ferroelectric behavior. And what is the structure of material? So at temperatures below Tc, then what you are going to observe here is, so if I cool temperature below 120 degrees Celsius, then titanium ions shift to one side of body center, and neighboring oxygen ions are also getting shifted. Then centers of positive charge due to titanium cation, which is positive ion, and centers of negative charges due to oxygen ions, they are shifted or they are separated by a small distance. Okay, so now what happens to titanium ion and oxygen ion? Now they won't clinch to each other, but they move little bit far away from each other. As a whole, what happens to the structure? Now it won't be cubic. So at temperatures less than Tc, then this cubic structure, it gets changed to tetragonal structure. Okay, so structure, it gets converted to tetragonal. If you take cubic unit cell, in cubic unit cell, all these sides will be equal. And when we talk about their angles, alpha is equal to beta is equal to gamma, which is equal to 90 degrees. But when we come to tetragonal structure, A is equal to B, not equal to C, but alpha is equal to beta is equal to gamma is equal to 90 degrees. And in tetragonal structure, what you will observe here is this titanium ion, okay, it will be little bit far from this negative oxygen ions. So now they are in the state of dipole. Because they have dipoles, there are dipole moments. So that's why what you are going to observe here is your barium titanate, it will be in ferroelectric state. And in ferroelectric state, what is its structure? Its structure is tetragonal structure. This is how we can understand how a material gets converted from one state to other state. And as you can see here is this ferroelectric behavior and paraelectric behavior, they are very much dependent on structure of a material. So when your barium titanate is in ferroelectric state, its structure is tetragonal, and when it is in paraelectric state, its structure is cubic. Now finally, I am going to end my session by discussing different applications of ferroelectric materials. As I told you in the beginning of my video, these ferroelectric materials are functional materials which have got many applications. And why they have many applications? Because of their property of retaining polarization even if their electric field is zero. And also these ferroelectric material, they have very high dielectric constant at Curie temperature. So if you take ferroelectric materials, because they have high dielectric constant, so that's why they are used in small sized capacitors to produce large capacitance. We know that capacitance, it is dependent on permittivity, and because they have high dielectric constant, so they are used in capacitors in order to produce large capacitance. And they exhibit hysteresis property. That's why they are used as memory devices. Why memory devices? Where data can be retained even if power goes off. And these ferroelectric materials, they behave as piezoelectric materials. What are piezoelectric materials? If I apply pressure to these ferroelectric materials, if they are strained, then these, not only temperature, we said that polarization takes place with application of electric field, or polarization takes place with application of temperature. But here we are talking about polarization takes place on application of pressure. So it means that your mechanical energy, it is getting converted to electrical energy. So this is nothing but a transducer where one form of energy is being converted to other form. So such transducers, they are used to produce and detect sound waves. Usually they are used for ultrasonic waves. And these pyroelectric behavior, because it is found in ferroelectric, so they are used to detect infrared radiations because they have this tendency of detecting light. Pyro means here with respect to temperature, polarization is changing. In piezoelectric material, polarization takes place on application of pressure, but in pyroelectric material, polarization takes place on application of temperature. Temperature sensitive ferroelectric materials or pressure sensitive ferroelectric materials. So because of this, they are used as sensors, as I told you, and also as actuators. Apart from this, they are also used in electromechanical filters. So these are some of the applications of ferroelectric materials. I hope you are able to understand better about the ferroelectric materials, what are their features and how they are being used in day-to-day life. So with this, I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.